Well, good morning, everybody, and welcome to this Altecnic and Cibse West Midlands CPD Day. We are going to make a start now. We're going to go through just a little bit of housekeeping first, if possible. Today's CPD, obviously, we're going to cover thermostatic mixing valves. But as we said, a little bit of housekeeping first. And first of all, thank you for joining this Altecnic CPD Day. And we deliver this in partnership with Cibse West Midlands. The Cibse West Midlands region aims to expand the knowledge of its members through various learning initiatives, and we hope to find today's topics insightful. Just a little bit of courtesy to the speakers and the participants. We politely ask that all delegates to mute when not talking, and to note that anything written in the chat can be seen by all of us on the call. This is an open forum, so anything you do make put into the chat will be seen by everybody else that's in the call. We will offer a Q&A at the end of the CPD, so feel free to ask any questions. Please write any questions into the chat box, or raise your hand should you want to ask a question as we go along, and I'll try my best to get to you as we progress through the CPD. Following from the CPD completion, you will be issued with a CPD certificate for your attendance. So you'll get that via email, I believe, once the CPDs have been completed. So the course objectives till today, hopefully at the end of this presentation today, there's a number of things that will hopefully you'll understand when it comes to thermostatic mixing valves. And we'll sort of break it down. And first of all, we're going to look at what are TMVs, why do we need them? I think it's important to understand that, the classifications that sit around them, the regulations surrounding TMVs, the installation, servicing, troubleshooting, and then we'll have a look at a little bit of a conclusion towards the end. So, like I say, feel free to ask any questions as we go along. I'll do my best to keep my eye on the screen when it comes to people raising hands or anything that goes into the chat, should questions be asked. So I've got a colleague with me who's monitoring that as well, so hopefully we won't miss anything as we go along. So, first of all, if anybody is not aware of Altecnic as a company, we are part of the wider Cleffi group. Cleffi is still a family-owned, third-generation-owned family business based in Italy. We're based just north of Milan. UK-wise, we turn over about 60 million. As a group, as an organisation, we turn over just over half a billion, so just shy of 600 million euros. And we are predominantly a manufacturer of brass components, but we have other ranges of products in our portfolio also. So back to the topic in hand today, which is thermostatic mixing valves. They do have a very varied application of where they can be used. And you'll find them in most buildings or anywhere where we need to blend sort of hot water down to a usable temperature. Anything from sports and leisure, multiple occupancy, industrial, healthcare, new build, commercial, education, offsite care homes, all these sorts of areas are where we tend to find thermostatic mixing valves. They do have different sort of regulations that surround them depending on the installation, something that we'll look at as we go through the presentation. But anywhere where we need to use safe hot water for bathing, for washing, there will be a TMV installed in some form or some nature. Domestic water systems, they're obviously become with a higher risk. And while we find domestic water systems in a wide variety of properties, there is no doubt that some applications require greater consideration, where we may find vulnerable users as the scald risk is therefore increased. And those are things like schools, things like healthcare and social care as well. Healthcare is a big one. It's something that we'll take a look at further through the presentation. But obviously where there are sort of vulnerable people, it's really important that we offer that scald protection by use of thermostatic mixing valves to go across those. Some of the challenges that we come against, obviously, water is a living, breathing thing, and buildings are living, breathing things, and the way that the buildings are constructed and the way they're used all have an impact on them. So, the locations and the materials of the buildings, as we see more and more construction going across now, the makeup of buildings is vastly changing. Everyone likes these big glass buildings now. Obviously those come with their own challenges when it comes to controlling temperatures, and those temperatures obviously relate to the water systems as well. But generally, we build with brick, we've got glass, we've got timber, insulated cladding, all types of different materials that we use to build buildings nowadays. All of those have an implication on how the water systems work. We think about environment as well. I know it seems silly, but think about the way the building faces. A safe facing building is going to have a lot more heat throughout the day. We have to then control the temperatures, whether it be for comfort or whether it be for water temperatures. We have to control those in different ways. Construction refurbishment. So extending or developing existing premises can mean existing rooms or repurposed. The existing water systems may be capped off and no longer used. Big problem when it comes to bacterial control is where we reuse or we renovate areas and we just cap off and we don't necessarily think of the water system, how we can remove the need for dead legs, or remove dead legs from the system, or maybe not be able to thermally pasteurize because we can't get those hotter temperatures down to those areas. Older buildings, again, bring their own challenges. Historical buildings bring along additional challenges. They may have hot water generators, which may not provide consistent supply or fluctuating temperatures. You know, one thing we always think with thermostatic mixing valves is we need to keep the water as hot as we can and keep it moving, but also keep it as cold as we can and keep it moving to get a good blend. So all of these become challenges. You know, the way the building is built, the location of it, how we're doing it. Is it new build? Is it refurbishment? And obviously the age of the building as well. So all of these do have an impact on the thermostatic mixing valves and the water systems within them. Problems that we have, you know, we do have conflicts when it comes to the use of thermostatic mixing valves, and that is kind of bacterial versus scald protection. You know, waterborne pathogens are a big issue. We talk a lot about bacterial control or Legionella control or Pseudomonas. All those kind of things, you know, can be controlled by temperature. So the causes where we get waterborne pathogens are things like stagnant water, biofilm, warmer ambient temperatures, organic matter resulting in Legionella, Pseudomonas. All these sorts of things have issues. The transmission is through water and through the air, so we get thermal gains, thermal losses, you know, but also that water system transfers those pathogens. The risks that we have when it comes to bacterial growth is things like immunosuppressed, so people who don't necessarily have a strong immune system can be very susceptible to bacterial growth within water. The elderly, again, you know, they find it more difficult to fight off infection. Infants and children, their immune system may not be up to speed yet, but also disabled people as well. They do have, you know, they have implications which could also cause some problems. The results that we have is pneumonia, Legionnaire's disease. You know, it can, in some cases, lead to death. So it is very important that we understand how water pathogens and how bacterial growth in water can be dealt with. The control measures that we put in place is chlorination, copper silver ionisation, ultraviolet or temperature control. So there's different ways that we can use various types of chemicals to dose a system. That again comes with its own challenges. If you've got sort of certain valves in the system, if you're chemically dosing, we have issues there where the materials inside the valves can start to degrade because of the use of chemicals. Copper silver ionisation again is another way of controlling that bacterial growth. Ultraviolet, very simple way, passing it through a UV filter. But temperature control, you know, is an effective way because we can see what those temperatures are. And we know the impact that the rising temperature has on killing those waterborne pathogens that are in the system. So we look at the flip side of it. You know, we talk about keeping the water hot. We want to keep the water above 65, 70 degrees to kill those pathogens. That obviously then leads to a water risk, you know, and where we have issues there. Transmission generally is part of the body or whole body immersion. A lot of the water standards or a lot of the standards that are built around thermostatic mixing valves comes around the body in full immersion. Full immersion of a body into scalding water is probably the most dangerous and can lead to catastrophic injury, but also can lead to death if you know, depending on the patient that's going to the water. The risks that we have, neuropathy, elderly infants, children, those with physical or mental disabilities, the visually impaired, learning difficulties, and those who present potential to harm to others. The reason that we class those as risks, people with obviously physical disabilities, it's more difficult for them to react to situations. Say, for instance, if someone was lowered into a bath of scalding water, if their movement is impaired, it's more difficult for them to get out. But also people with mental disabilities, their perception of risk is far different to what ours is. You know, putting their hand in the scalding water may not have the same reaction to what we may have. They don't see it as a risk. They don't necessarily feel the pain the same. It can lead to real problems. So we have to cover off all these different sort of scenarios when it comes to protecting people. The results that we have, first or second or third degree burns, psychological impacts, skin grafts, scarring, and like I say, no, it can lead to death as well. But the way that we can control it is by thermal control or thermostatic control, which is what we're going to take a look at today as we go through this presentation itself. So some of the guidance and the legislation that sits around it, there's plenty out there. There's lots of documents that you can refer to, that you can read up on, that you can gain your guidance from. So things like the Water Management Society, that's the guidance of scald risk assessment and domestic water systems. The Health and Safety Executive, so the HSE, that's the approved code of practice, and L8, that's the Legionnaire's disease, the control of Legionella bacteria in water systems. The Health and Safety Guidance of HSD 274, that's parts 1, 2, and 3. That's Legionnaire's disease, that's technical guidance. NHS estates, the Health Technical Memorandum, so HTMO 401, the control of Legionella in healthcare premises, and that's a code of practice. There's British standards we sit around there, so BS 8680 2020, it's the water quality, water safety plans and code of practice. The British standard of BS 8580 2010. The health building note, which is 00-01, that's designing health and community care buildings, so how we design safety into systems. And the building regulations approved document Part G, that's sanitation, hot water safety and water efficiency. So there is plenty of guidance out there, or codes of practice, shall we say, or standards which sit around the control of water within buildings. So safe water temperatures, so further guide and emphasis this. So NHS England, never events are largely preventable patient safety incidents in which the risk of scalding for vulnerable patients is one. The BEMA recommends a code of practice for safe water temperatures. Building owners have a duty of care to all users, especially if the occupants are regarded as high risk. The onus of responsibility is with them to make sure that there is a safe environment for all users. So we can see there, if you're a building owner, you've got a duty of care, you've got to ensure that the safe working conditions of the systems that you have cover all eventualities we looked at in previous slides, whether it be healthcare, elderly, infants, disability, disabled, whichever it may be. We have to make sure as a building owner, you know that you are there. Never events, again, it sounds like the same thing, but we put these procedures in place. There's a lot of talk, say, for instance, in healthcare, that we don't get scolds. There are never events, but because there's already implementations been put in place to ensure that we don't have those accidents. So, a never event is something that we're trying to prevent by putting safety measures in place. So we've mentioned scalding, and we've looked about what the risks are, and it is quite stark, really, if you can see the chart on the screen now with the speed of burns and the depth of burn. So we talk about first, second, and third degree burns. A first degree burn is where we just see the surface. So you may, if you suffer a first degree burn, you tend to get sort of redness of the skin. Something like sunburn could be classed as a first degree burn. When we look at second degree burn, it's the depth of the burn that starts to change. So as we go down to a second degree burn, we go down to what's called the dermis, which is kind of where your hair follicles start to produce hairs in the body. So it's a deeper burn. Then we're going to start to see blistering of the skin, things like that. That's where we start to get a different depth. And then third degree burns is where we go all the way down to the deepest parts of our sort of fatty tissue, and that's where we get some real scarring. If you ever see people who have suffered serious burns, you know the scarring looks like. It normally results in things like skin grafts or ongoing treatments to sort of aid the recovery. So first and second, third degree burns, it's all about the depth of the burn and how deep it goes into the skin. And I think one of the most stark things is the time and exposure of burns. If we look at some of the water temperatures on there, if we take a child, say for instance, for a third degree burn, the time it takes at certain temperature, I think it's 0.5 or 0.25 seconds at 60 degrees. It's instantaneous. We put vulnerable people into scalding water. The time it takes is so minute. And if you think the time it takes for someone to get into a bath, realise the temperature's too hot and then get back out again, by that time it could be too late. It could be a second or a third degree burn, depending on the patient, depending on the person. The reason that the elderly and the infants or younger people are more susceptible is because their skin is so much thinner. As we grow up, our skin seems to get a lot thicker, gets a lot more robust. But obviously, as we're younger, it hasn't gone through that stage, and as we're older, it goes in the reverse. It starts to become thinner, so hence why the reason that the elderly and the infants are more susceptible to this. So yeah, it's just a stark reminder, really, when you look at the time of exposure and how quickly you can suffer those burns, even at like what we class as tap temperatures. Someone's had, for instance, it's got 50 degrees. A child, 45 seconds in 50 degree water can suffer second degree burns. So it's really important that we look at the temperatures and make sure they're safe for the application that we're using. Is it a bath? Is it a hand wash basin? Is it a shower? Is it a bidet? All those things should be taken into consideration. So some of the statistics that sit around it, scald statistics, not just a risk, there's a lot more that goes with it. So 5,000 serious injuries from scalding water every year. 85% of deaths and incidents occur to children and the elderly. It's just over £170,000 the average cost for NHS to treat a major burn, so the financial implications are very high. 34 injuries resulted in death from the scalding itself. It may not be as a direct result of a burn per se, but the impact it has on the body itself once you've gone through that burns process is where it leads to death. 43% of scalds equate to the most common burn injuries, and 1,400 incidents result in overnight stays in hospital. So, we look at the cost of the NHS, we look at the result or the strain it can put on the NHS. It's a preventable scenario. So we have to make sure that we are, that we're taking care of it as best we can by using thermostatic control. So need to control, legacy of thermostatic control. So since the 1990s, a method to evaluate and certify anti-scalding temperature control devices was in high demand. This was both in healthcare and the domestic markets. This demand escalated in the late 90s when the United Kingdom National Health Service, or the NHS, required an enhanced and robust test regime for thermostatic mixing valves, or TMVs, that could react to cold water failure. The NHS model engineered specific DO8, that's performance criteria, includes low and high pressures, mixed pressures, thermal shutdowns, testing of hot spikes, and a need to evaluate for similar devices for a general residential housing market came in 2010. So it was all very much driven by the NHS. There's always been some kind of mixing, shall we say, of mixing water, but we needed something a lot more strict or more stringent to be able to actually quantify what we were doing and put some performance standards about it. A lot of it is about temperature stability. So if we are saying that we are delivering 40 degrees from a thermostatic mixing valve, we ensure that we are doing that, and the test standard makes sure that that is the case. But also the anti-scalding, which is one of the biggest features of a thermostatic mixing valve. So should the cold supply be interrupted, we have to ensure that scalding water isn't passing through the outlet of the mixing valve. So we do that by what we call a thermal shut-off. And the performance of that thermal shut-off is key to the standards and the performance of these valves. There's a couple of documents that you can see on the right-hand side there where you can see that have actually been instances. It's not just hearsay. We're not just making it for the sake of a presentation. These are real true-life instances that have happened where it could have been prevented by the use of thermostatic mixing valves. So scald prevention, we've spoken about we want to keep temperatures as high as we can to try and reduce the risk of pathogens or bacterial growth within water, but that leads to its very own issues with scald protection as well. So we have to try and protect that as best we can at point of use or depending on however we're using a mixing valve. If we look at the temperature of water, so 20 degrees or below, the bacterial growth, it will remain viable, but it will remain dormant. So it doesn't mean it gets killed below 20 degrees. It will still be there, but it can't multiply, which is what we're trying to protect against when it comes to bacterial growth. The optimum growth for the bacteria is anything between 20 and about 42 degrees. 37 degrees is optimum. That, of course, is our body temperature, which is why it's so dangerous when we do start to get bacterial infections from things like Legionella, and they can multiply within the body. That's why we become quite poorly with it. If we then start to increase temperature, so we've got, say, for instance, 50 degrees, it takes about 2 hours at that temperature to start kill off the bacteria. As we increase again to 60 degrees, we're going to get a 90% kill of that bacteria in about 2 minutes. And then obviously we raise it to 70 degrees or above. We class that as an instant kill because the bacteria can't survive in those temperatures and we are actually killing it off. So you can see, obviously for bacterial growth, we want to keep the water as hot as we can. But for scald risk, we need to keep it at a safe temperature. There's a conflict there. Hence why thermostatic mixing valves become really important key parts. And you can see why some of the safety features, such as the cold water shut-off, do become really important because we don't want to pass that scalding water all the way through to the outlet. So thermostatic mixing valves will prevent that. So how it works, it's quite simple, really. There's no real sort of wizardry which goes on inside a mixing valve. I know sometimes when I do some training, people think that there's all sorts that goes on there, but it is very mechanical in the way it works. We essentially take a cold supply temperature, we take a hot supply temperature, and we mix that to give us our mixed outlet. It's all done by thermostatic control. So there's a thermostatic element which sits in the valve that expands and contracts as the waters flow over. It sits in the mixed outlet, so we can measure what those temperatures are, and it will just regulate to allow more or less hot or cold water through to ensure that we're delivering a safe temperature. When we talk about the thermal shutoff, what will happen if the cold water was to isolate and the hot water was to pass solely over the thermostat? It becomes very hot very quick. It reacts very quickly, expands. That expansion pushes a pin and it closes down the inlets to it, so no water should pass through. So that's why we look at it when it comes to thermal control. But it's very simple. We take cold water, we take hot water, and we blend it down to a safer temperature, as we can see there through that cutaway example on screen. So with the internal components that we have in thermostatic mixing valve, obviously we've got the protection cap. The cap is in there to make sure that that nothing can damage the valve, but also it can't just be adjusted or damaged, by mistake. The headwork and the O-ring. The headwork is where a lot of the work takes place. That's what modulates. There's a spring in there. That spring pushes down. There's actually 2 springs inside the mixing valve, and they sort of work against each other. So as the temperature expands and contracts, it pushes the springs up and down, it regulates the temperature. We've got the flow conveyor. The flow conveyor is controlled by the headwork. That again modulates up and down to allow more or less of the hot water to come through. Check valves in each side of it to prevent any kind of contamination through the hot through the cold, or cold through the hot, shall we say. Either way, check valves there to protect against that. A strainer to prevent any particles passing into the valve. It is moving, it does constantly regulate and move. Any small particles in there can have a real issue in the performance of the valve. It can cause them to stick and not perform as they should do. The thermostat, an obturator. So the thermostat is what gives us that temperature control. Again, it works off expansion and contraction. As it expands and contracts, it pushes the pin up and down, which allows the flow conveyor to move. Then we've got the bottom spring as well. So we've got two springs with two opposing forces that work against each other, but with each other at the same time to ensure that we get that safe temperature. As we adjust the top, so underneath the cap is the adjustment knob. As we adjust that knob, what it does, it changes the tension of the top spring, which moves obviously the parameters of the valve itself. So let's say there's no real wizardry that goes on in there. It's very mechanical, but it's very clever the way it works. So some of the regulation that sits around it, or regulation 4, within the water supply fittings regulation 1999, regulation 4 details the specific requirements of the components which form water systems. The water fitting regulations set out the design, maintenance and operating standards required for the plumbing systems in all types of premises to protect the public health and safeguard supplies and preventing either waste, misuse, undue consumption or contamination. So those are the things that we look at. We always traditionally look at regulate or Reg 4 as RAS, but there are other ways that you can now show compliance to Reg 4. So you've got the RAS approval, you've got an NSF Reg 4 approval, and you've also got Kiwa Reg 4. So as I said before, traditionally people always direct straight to RAS, but all RAS does is show compliance to Reg 4, of which now other standards will approve to the same as well. So a bit about regulation. We'll talk about RAS approval certification. It's all about compliance to that regulation 4 of the Water Act. So the approvals which sit around thermostatic mixing valves, or the thermostatic approvals, is third-party testing accreditation. One of the two terms that we hear about is TMV2 and TMV3. TMV2 is solely designed for the domestic market, so where you'd have one in your individual property or somewhere that's outside of healthcare. We have two standards there. You can see BSCN 1111-2017 and BSCN 1287-2017. But those are the two test criteria that we have to manufacture and test the valves to. One is high pressure and one is low pressure. So it's anything below half a bar, anything above half a bar. It's how the valves perform at low pressure and high pressure. So always look at when looking for accreditation that it's got the two standards, so 1111 and 1287. It ensures that you can work to both high and low pressures. TMV3 is solely based for healthcare. You've got BSCN 7942 is the British standard that we test and manufacture to for that, but also it's driven by HTMO 401 and D08. So it's driven by healthcare. A lot of the valves that you see on the marketplace are approved to TMV2 and TMV3. You will see some that are solely designed for TMV3. And a lot of the differences that come around between the two standards is under the fail-safe conditions. So where we look at when a valve fails, or when the cold water fails, we say how the valve will perform under those conditions. But those are the two standards you should always look out for. So the TMV2 NSF scheme 2 and TMV NSF scheme 3. So TMV2 is domestic or anything outside of healthcare. TMV3 is solely designed to work within healthcare itself. So fitting the right TMVs, there are three main types of thermostatic mixing valve, and ensuring you fit the right valve in the right application is key for this. So first of all, we have a heat source, or DTC, or direct temperature control. Now, what these are designed to do is take hot water stored temperatures. If you're storing waters of 80 degrees and above, for whatever reason it may be, we would use a DTC valve or direct temperature control valve to blend that temperature down to, say, for instance, 60 degrees, to circulate around your system to then bring down at point of use. So it's designed to make higher flow rates, but take higher temperatures from higher stored water. Group control, as by its very nature, its name is where we used to design to use multiple outlets. That could be things like communal showering, changing rooms, all that sort of stuff. Anywhere where we need to run more than one outlet, where we'd use a group mixer. They're designed for multiple applications. They've got higher flow rates. They offer good temperature stability. But if we think back to where we were with bacterial control, obviously, so for instance, if it's a football club, the showers may only be used once a week. And so you have to design into your system ways to sanitize that system away from it, because you're creating dead legs by its very nature. So always design into the system a way of sanitizing through that should you be using group control. And then obviously point of use kind of says what it does on the tin. Designed for single point applications such as individual showering, hand wash basins, bathrooms, etc. They offer a high level of protection against scalding and thermal shock. So you tend to see these ones installed either under your bath, under your sink, under a bidet, maybe connected to a shower. So we have to make sure that we use the right ones, so we say, so the right thermostatic control for that is key. You can set the safe point of use if you've got two, say for instance, two sink outlets which are installed back to back, and there's no great length of pipe work. You may get away with using one single mixing valve to feed the two, but we'd always like to see one per outlet to ensure we're offering the best amount of control. Installation wise, so criteria and challenges. Once you've verified that the installation pressures and temperatures are correct, it's important that the physical supply infrastructure is in place to support the TMV's operation. This is really key. From a perspective of myself as a technical manager and my team, a majority of calls that we get to deal with things with issues with thermostatic mixing valves are key to, is the system itself. It's the way that the system actually performs. So we have to make sure that supply pipe work has been flushed appropriately to remove any debris that could potentially affect the TMV. Isolation valves, preferably local to the TMV. Obviously for maintenance, for testing, we want to be able to isolate them pretty close. Inline strainers, they're normally supplied within the TMV, within the connections, so you'd have it within the tower pieces. And the mixed outlet pipe work is as short as practically possible. We have to really consider that when it comes to the install, keeping that pipe work as short as possible. Again, we talk about bacterial control. We don't want to create a dead leg, but we also want to have the best control we have, by keeping the pipe work as short as possible. Manufacturer's minimum flow rates is adequately achieved through the normal operation. So make sure that the minimum flow of the valve is achieved. If it's not, you will get instability in your temperature. So make sure that those flow rates are achieved. If the mixed outlet has been flow restricted, it's in a position which will not affect the performance of the TMV. Quite a common one, as we try to preserve water, there's a lot of taps now which are like low flow or ultra low flow. They'll have a flow restricting the outlet. The issue that we have with that is if it's too low, the thermostatic mixing valve cannot shift the amount of mixed water out of its body quick enough, and it will start to back up, which means that the mixed water that we're trying to get rid of then sits in the body of the valve. It then can't regulate its temperature properly, it gets confused. So we've always got to make sure that we've got a strong, good amount of flow leaving the valve to ensure that we offer it the best chance for it to perform when it's doing its thermostatic mixing. So just some things to consider when it comes to that. And then there's like a little circle there, are you using high pressure, are you using low pressure? Have you got the right supply temperatures? Have you got the right supply pressures? Is it a balance valve? Do you need equal balance from the hot and cold coming in? Can it work, as an imbalance? I know some of the valves in the market will only take, balanced pressure, so 2-bar and 2-bar, hot and cold. Others on the market will have, like I say, for instance, a 5-to-1 ratio, so you can use 1 bar of cold, 5 bar of hot, or vice versa. So these are some things that you need to consider, when you install it, and making sure that you've got all of the operating parameters there that we need to be able to perform the valve to perform to its capabilities, essentially. So a little bit of installation wise. So we looked at the 3 different types. So we looked at a DTC or direct temperature control or tempering valve, generally installed in a hot water cylinder. So you take the hot water out, the cold water, and you send a mixed temperature. You can be used it with a recirculation loop, and you can use it on a recirculation and cylinder return. So you've got the options there. When it comes to direct temperature control of DTC or tempering valve, you've got different options for install there, but we are generally there taking temperatures of 80 degrees and above and reducing those down for circulation. Group control, again, we've spoke a little bit about how they work. It takes that larger flow rate, it produces it, or it passes it through multiple outlets. But again, you've always got to, you've got to be conscious that you've got to be a way to sterilise that pipe work and make sure that we're not creating or building a dead leg into the system, shall we say. We do get very common questions. So, well, how many showers can I run off a group mixing valve? The question is your flow rate. How many flow, or what is the flow rate that the shower is achieving each individual head? We always size them off a worst case scenario. So we always size it off the fact that every single outlet will be running at any one time. If we can satisfy that and it's worst case scenario, then we know that the valve will work as it goes through its operating window if there's less showers used. There is also the option for group mixing to use what we call a hybrid mixing valve or hybrid mixing valves. Those are still work as exactly the same as a thermostatic mixing valve would, but they have a hybrid control of electronic pasteurization. So what they will do with a timed process is you can take hot water from the cylinder. So you can take your pasteurized hot water and you can pass that all the way through the system. So what I mean by that is you can thermally pasteurize your system at a time when the system is at little use. If you've got a building which has got the potential to be running for 24 hours a day, it's probably not the product that you need because you could potentially send in, scalding temperatures around. But if you've got buildings that shut down overnight, or somewhere you need to pasteurize the pipework and there's not going to be an outlet used, you can use things like a hybrid mixing valve to be able to thermally pasteurize your system with electronic control linked to the BMS. You can see it's been done. You've got records of it. So a couple of options there when it comes to group mixing. The standard group mixing valve and also the hybrid mixing valve also. Then finally, the point of use application. These should be installed in accordance with the manufacturer's instruction first and foremost, and consideration should be made to the fitment location where the valve will need to be maintained regularly to ensure correct operation. The complete installation should consist of appropriate isolation and integral strainers. Mixed outlet pipework then should be as small as feasibly possible. So HTMO 401 published by the Department of Health, paragraph 9.49 reads as follows. Particular attention should be given to ensure that pipework containing blended water is kept to the minimum. Generally, downstream dead legs should not exceed 2 meters and the complete length of the spur should not exceed 3 meters. So what I mean by that, if you don't want it in 2 meters of distance away from where the outlet is, but 3 meters of permissible pipework, so you may have elbows or bends which are in there, but we're really trying to shorten the length of that dead leg as much as we can. So point of view, as it shows on those diagrams, as close to the outlet as possible is what we're looking for. We're just reducing the risk of dead legs and when it comes to the bacterial control within the systems there. So from a commissioning process, we have to follow what we say. So first of all, we've got to make sure that the system is clean, flushed. There's nothing in there that could be harmful to the system. Set the mix temperature using a calibrated thermometer. So we can set it. We hold it under the mixed outlet. We can set the temperature simply by turning the adjustment knob either clockwise or anti-clockwise once we've got the right temperature. And depending on the intended use and the associated risk, the outlet should be regulated as to accommodate accommodate fluctuations over time. So if you want to guarantee you don't want to go anything higher than 48 degrees, and you have to take that into consideration, so we say, when you're setting those. If the thermostatic mixing valve is connected to more than one outlet, then the outlet should be checked to verify the stable temperatures, which expose to its worst case scenario, which is obviously all outlets running at any one time. If necessary, complete thermal safety shut-off in accordance with the relevant standards. So carry out your thermal shut-off. There's a lot of talk around thermal shut-offs in what's permissible allowed. Some people think it should be shut off completely. Some people say it's a Coke can's worth of water. Some people say it's an egg cup. There are multiple different, rumours to be said that are used. It is written into each individual standard what it should be. I think for a bath outlet, it is 500 millilitres for the first 5 seconds, then 400 millilitres for a further 30 seconds. So it's 900 millilitres in total. For a bath, for a sink, it's small. I think it's 300 millilitres and then 200 millilitres. In healthcare, again, for TMV3, it's different again. It's very much time versus temperature. The hotter the water that passes through the outlet under the thermal shutoff, the quicker it should shut down. If there's only a fluctuation, if you isolate the cold and the water current tap is still 42 degrees and you get it set to 40, it will permissibly run on forever because it's not deemed to be an unsafe temperature. But should that water spike by 10 degrees, it's 0.25 seconds is the shut-off time. So again, read the standards. Don't go off hearsay. Don't go off what your mate told you, who's done it for years. Make sure you're doing to exactly what the standards state. If the thermal shut-off test fails, then establish the cause through checking the installation supply to make sure your hot water is hot. Always make sure as well that the hot water is 10 degrees hotter than what the mixed temperature is. So if you want a blended temperature of 38 degrees, your hot supply must be 48 degrees as a minimum, and your cold temperature must be 28 degrees as a minimum. So we're always looking for a 10-degree delta either side of your set point. Record the information is key. It's always important that when you're setting thermostatic mixing valves, you keep a record of what those are. That's for if you're no longer going to be working on that application or on that site, somebody can come along, look at those records and see what those valves should be set to, and they're not guessing or not adjusting temperatures outside or away from where they should be set. Duplicate the records and pass on to a responsible person. So if you're an FM company or a MAB, you You take those temperatures, you read them, you record them, you then pass them on to a building owner. So should a third party or somebody else come in, as we say, they've got records where everything should be set to and there's no misconception of where we should be. A little bit of recommended temperatures as well there for wash and basins 41 degrees, showers 41, bidets 38, bath fill 44. But again, depends on the application, depends on the scenario, depends on the intended usage as well. So just a little bit of recommendations there when it comes through to those. Maintenance wise, you know, that they are valves that should be maintained. This is the key, and it says it in the installation guide. Make sure they're accessible. The amount of times I've visited sites where they've been boxed in, put behind IPS panels, or they've been tiled in so you can't actually get to them. We need to be able to maintain the valves. That includes removing the cap, removing the body, so the headwork, removing the internals of the valve. So always make sure that we've got, you know, an acceptable amount of space for them to work on. But there's different ways to do it. So the fail-safe procedure, like we say, it's done in different ways. It's done for TMV2 and TMV3. Test criteria is set out in BSN 1111/2017 and 1287/2017. The maintenance intervals are annually. You can judge a maintenance interval by the performance of the valve. If you carry out all your checks on your valve, your temperature stability, your fail-safe, all that kind of stuff, if everything is as it should be, the valve probably doesn't need maintaining, but you're carrying out an initial check to see whether it does need maintaining. It's slightly different for TMV3, so the test criteria is set out in the DO8, but also in BS 7942. So maintenance intervals 6 to 8 weeks after it's initially installed, then a further check after 12 to 15 weeks, and then 8 to 21 weeks after that. And then it goes on to a rolling basis of performance of the valve. If the performance is falling off, if it's not holding the temperature stability, if the temperatures are dropping or increasing, or your fail-safe is not working, that will indicate then that the valve will need to have a service. When it comes to the fail-safe procedure, for TMV2, it's very much a case of we run the outlet, so we've got stable flow. We isolate the cold using the isolation valve, which is installed. We take a measurement for the first 5 seconds in a container. We then swap that to a second container, so we will have to have 2 containers. We then collect it for a further 30 seconds. So then we are reading that over a 35-second period for 2 separate containers. We then get the permissible amount of water which is allowed to pass through. When it comes to TMV3, it's very much with the temperature control. So you hold the thermostat under the outlet. You then isolate the cold supply. Should the water continue to run, you measure the temperature of it. You should be measuring the temperature of it. If that becomes, you know, as we said before, as that temperature increases, the faster the valve should shut off. I said it before, if you've got your valve set to 38 degrees, you carry out your thermal shutoff or your cold water isolation, and that valve then permits to pass at 40 degrees, only 2-degree increase. It's not perceived to be, it's not going to be a scalding risk, so the valve won't shut off. But if there's a 10-degree increase, it drops down to 0.25 seconds. So it's very much testing the temperature of the water, which is coming out of the outlet. So a little bit on the maintenance procedures and on the fail-safe procedure. Troubleshooting. You know, the main contribution to full thermostatic mixing valve operation is supply conditions, and we need to ensure that both the hot and cold supplies are within specification. These, as suggested previously, must have a hot supply inlet temperature of 10 degrees above the mixed outlet temperature and a cold supply inlet temperature of at least 10 degrees below the mixed outlet temperature. In lieu of manufacturer's instructions, everybody's work slightly different, so always rely on the manufacturer's instructions first and foremost. To see where they should be working. Provided the temperatures are correct, then pressure and flow may be an issue. These should be verified by confirming again to the manufacturer's instructions. We spoke about balanced feeds, so balanced pressures. Some will allow a pressure ratio, so check those are where they should be. If all the OK is above, we need to expose the working parts of the thermostatic mixing valve and check for debris. Now that we have the working parts exposed available, these should be visually checked for their integrity or for degradation, and the thermostatic shut along with any O-rings should be lubricated using a RAS-approved silicone grease. As we said before, the valve is constantly modulating. It moves up and down. We have to make sure it's free to do so. We can lubricate the valve to ensure that it's done. If we put it back together and it's still not functioning, obviously there's something seriously wrong. And if this is the case, if there's any kind of doubt, swap the valve. You know, it's a safety device at the end of the day. We don't want to run the risk of thinking, well, I'm not too sure it's working or not. Just change it out. You know, we're talking about skull protection here and making sure that people are safe within there. It's always key to remember as well that, again, we talk about supply temperatures. Always check that your raw hot water, the hot water coming to the fire, is at the temperature it should be. It's okay saying when it's set to circulate at 60 degrees from the hot water storage. That's all well and good, but is it 60 degrees at the actual inlet to your thermostatic mixing valve? So there's always a key. Is temperatures is normally the one that's the killer, or they've started to become dry. So adding lubrication is always key in that aspect. So as a bit of a conclusion, stop. What is the potential risk? What is it? What is the exposure? What's the outlet temperature? Think, identify the installation and apply the relevant condition standards. So is it TMV2? Is it TMV3? And then act, fit and commission. It's quite simple. Just work out what it is you're working. Is it healthcare? Is it inside healthcare? Is it not healthcare? And then, install the relevant valve for that standard. Is it group mixing, whatever it may be? And then advise, fit and commission it and make sure it's working as it should be. And that is in my presentation. I think I did see one question that popped up into the chat. So I will go back to that. Apologies, I've missed it before. Our regulation for TMVs, yeah, so it's a standard which sits across all the water systems. So we work to standards which are nationwide, essentially. So if you are working in, say, for instance, in Devon or Cornwall against the Northeast, it would be the same. We're offering school protection across here. We need consistency across the board, which is what we're trying to achieve by working the same, having the same standards that work. There's plenty of literature available on our website. If you want to head over to www.altecnic.co.uk, there's plenty of information on there on all of the mixing valves and literature that we hold on there, and also on the YouTube page, there's different sorts of information on there. So I don't know if anybody else has got any further questions. No. Okay, well, thank you everybody for attending our CPD today on thermostatic mixer valve. Everybody's name that has attended will be issued with certificates, as Helen just said. Again, I thank you all for your time and enjoy the rest of your day.